The James Webb Space Telescope captures infrared light using 18 gold-plated hexagonal mirrors, allowing us to see across billions of light years. Because light takes time to travel, peering into the deep cosmos means looking further back in time. Webb recently identified a class of objects known as little red dots. These unassuming crimson smudges are supermassive black holes, weighing millions of times the mass of our Sun, already in place just 400 million years after the Big Bang. To understand why this discovery creates a paradox, we must look at how these objects work. A black hole is a concentration of matter packed into a tiny space, creating a gravitational pull so strong that even light cannot escape. Standard physics suggests a slow, multi-stage evolution. Massive stars must burn out and collapse into small stellar mass black holes. From there, those seeds spend billions of years slowly consuming gas and merging with other black holes to reach supermassive proportions. The timeline does not support this. 400 million years is too brief for stars to live, die, and merge into giants. Finding these behemoths so early in the universe is like walking into a kindergarten classroom and finding a fully grown adult sitting at a desk. Solving this timeline requires a closer look at black hole anatomy, starting at the event horizon. This is the boundary of no return, where our current understanding of physics completely breaks down. Matter orbiting the horizon forms an accretion disk. Gravity warps space-time, folding light into a double-hump shape known as gravitational lensing. The disk spins near light speed, triggering Doppler beaming. The approaching side glows bright blue, while the receding side shifts dim red. Orbiting just above this flattened disk is the corona, a turbulent billion-degree cloud of particles moving at near relativistic velocities. Despite this violent environment, black holes are not cosmic vacuum cleaners. They only consume matter that crosses the event horizon. Otherwise, they exert the same gravitational pull as any star of the same mass. Because this consumption is a slow, restricted process, standard feeding mechanics cannot account for how early universe black holes grew so large in such a short window. Webb captured a violent cosmic collision in the distant universe. Astronomers named the Infinity Galaxy. Within this collision sits a massive black hole that isn't located in a galactic center. Instead, it is forming inside a dense, turbulent reservoir of gas suspended between two merging nuclei. This supports the direct collapse theory. Massive clouds of cold primordial gas bypassed the star-forming phase, collapsing wholesale under their own weight. This process instantly forges massive black hole seeds containing tens of thousands of solar masses, rather than starting as a single dead star. This mechanism provides the shortcut necessary for supermassive giants to exist when the universe was still in its infancy. For decades, models assumed galaxies formed first and slowly nurtured black holes in their cores. The reality is a reversal of those roles. These direct collapse black holes likely formed before their host galaxies, acting as gravitational anchors that pulled in the matter to build them. Our own Milky Way follows this same architecture, constructed around a central gravitational anchor named Sagittarius A star. While these remain dangerous environments capable of spaghettification, where gravity stretches an object vertically while crushing it horizontally, they are the gravitational skeleton upon which our universe is built. By staring into these dark and violent extremes, we are actually piecing together the origin story of our own existence.